So I mentioned in the last video that we're going to want to express our multiple linear regression model in terms of a vector dot product. So before we do that, let's revisit what exactly it is a dot product is. So let's suppose we have two vectors of length n, which for this example we will call a and b. The dot product of a and b is defined as being a1 b1 plus a2 b2 plus so on and so forth, all the way through an bn. So what does this really mean, or how do we get to this result? Well, we take the first element in A, multiply it by the first element in B, and add it to the result of multiplying the second element in A and the second element in B, all the way through the last element in A and the last element in B. So we're doing these element-wise multiplications and then adding together the result. One way to denote the dot product is with this circle, but the notation that we will use most commonly moving forward is this transpose notation. We can write the dot product of two column vectors A and B as A transpose B. The reason this works is because the transpose of a column vector is a row vector, and when you multiply a row vector by a column vector, the result you get back is just a single number. And conventionally, all vectors by default are column vectors. The dot product is only defined if two vectors that have the same length. So if A and B have different numbers of elements, then this process of taking element-wise products doesn't really make sense. Lastly, the dot product is a special case of something that you may have heard of called the inner product, which applies to things that are not just vectors, and there are a set of properties that inner products generally hold, but we don't really need those for our purposes. We will stick to thinking about things in terms of the dot product. Now you may be wondering, who cares? What does this have to do with our model? Well, our multiple linear regression model looks awfully similar to a dot product. We have parameter times feature, plus parameter times feature, plus parameter times feature. So if we stack all of our parameters into one vector and all of our x's into another vector, we can express our multiple linear regression model as just being the dot product between our parameter vector and our x vector, which contains all of the features for a single observation. And so that's what we've done here in the bottom left. If we stack all of our parameters into a single vector containing theta naught, theta 1, theta 2, all the way through theta p, and we stack all of our features into a single vector, so we have a vector containing 1, x1, x2, so on and so forth, all the way through xp, our prediction is just the dot product between x and theta, which here I've denoted with x transpose theta. So one thing you may want to do is pause the video and verify for yourself that this dot product between x and theta, the way that they're defined here on the slide, does indeed evaluate to the same multiple linear regression model formulation that we looked at earlier. So, this is great. We now know how to write our model in terms of a dot product, but, we know we're going to have to look at the mean squared error of our model, and at that point, we will want to be able to make predictions for our entire data set, as opposed to just predictions for a single observation. So this formula only really works when we are looking at a single observation from our data set. But how can we generalize this to include any number of observations? Well, we look at what's called a design matrix. So the design matrix, which we denote with this fancy letter X, contains several observations all stacked together in one big matrix. So the rows of our design matrix each correspond to a different observation or a different data point. So the third row, for instance, contains all of the features for observation 3. And so the value that we are trying to predict for this row is y3. Now, the reason the subscripts for all elements in this row start with a 3 is because the first sort of subscript is the row index, and the second subscript is the column index. So you can see, every element in this column has second subscript 1, and this one, everything is second subscript 2, and so on and so forth. So rows correspond to observations or data points. Columns then correspond to features. Now this first column of our design matrix contains the value 1 for every single observation, and this is what we call the bias column or the intercept column. The reason we have this is because our model has a term of the form just theta naught without an x attached to it. And so in order to get that intercept term, we need this column of all ones in our design matrix. This next column contains the feature x1 for every observation. So this is feature x1 for observation 1, feature x1 for observation 2, and so on and so forth. Let's take a look at a tangible example. So here's sort of what this data frame looks like when we take a look at it in a notebook. Pandas tells us that this data frame has 708 rows and 4 columns. That means we have 708 observations, or 708 data points. Using the formulation that we've described, we would say that this is 3 features plus an intercept term. And that would match this definition here. So let's just say this is 3 features plus an intercept term. So for instance, this row right here corresponds to every feature for observation 3, right? So the field goals for this player is 1.1, the assists for this player is 1.9, and the points for this player is 3.2. So these are all of the features for one player. The field goal column corresponds to all of the field goals for every player. So that's how we interpret rows and columns of our design matrix. Now, putting this all together, the way that we can make predictions for our entire data set at once is by taking our design matrix X, which has dimensions n by p plus 1, right? 708 rows and 4 columns. Here n was 708 and p was 3. And multiplying it by our parameter vector theta, which has dimensions p plus 1 by 1, right? The parameter vector theta contains the weights for each of our p plus 1 columns in the design matrix. And we will look at a tangible example of that momentarily. But you may see now that these inner dimensions match up for us to do multiplication. The dimensions of our design matrix are n by p plus 1. The dimensions of our parameter vector are p plus 1 by 1. And so these inner dimensions collapse. And the result of this multiplication on the right-hand side is a vector of size n by 1. And that vector is what we call y hat, which contains our predictions for all n data points. And so we call this our response vector. It's a vector containing all of our y hats. Let's take a closer look at that. So here we have our design matrix X, our parameter vector theta, and our response vector y hat. A couple pieces of notation. Moving forward, xi comma colon, or xi, will represent row I of our design matrix. I comma colon sort of mimics the way that we use loc and iloc in pandas, which is saying give me row I and all of the columns for it. So for example, x2 would represent this row right here. It would represent 1, x21, x22, all the way through x2p. X colon comma j will represent column j of our design matrix. So this is saying give me every row but only column j. Now let's zoom in on a calculation. Let's suppose we want to compute y2 hat, so the predicted output for the second observation. Well, by this matrix multiplication, the way we compute y2 hat is by taking the product of the second row of our design matrix, so this right here, with our parameter vector theta. And so, we know from before that that result is theta naught plus theta 1 times x21 plus theta 2 times x22, and so on and so forth. The reason this looks slightly different than our model before is because there's a 2 added in front of each x, which represents the fact that we are looking at the second observation. Another way that we can express this calculation is as the dot product of the second row of our design matrix, so x2, and theta. The reason it's transposed is because x2 is a vector, it's a column vector. Even though it's represented as a row here, vectors on their own are always columns. So we transpose it and then multiply it by theta. This represents the dot product of the second row of our design matrix and our parameter vector. And these representations are equivalent. So let's go back to the NBA data set that we were just looking at. Let's suppose we want to predict y2 hat, so the predicted output for the second observation. And let's just use this made up parameter vector theta that I just came up with. The way we compute y2 hat is by taking the dot product of the second row of our design matrix with our parameter vector theta. And by doing that, the result I get is 0.1. So here, for this parameter vector, it might not be the optimal parameter vector, but the way we would predict our second output is with this dot product, and the result would be 0.1. So what if we want to predict outputs for all rows of our design matrix? Well, we can do that by matrix multiplying our design matrix with our parameter vector. And so now, instead of doing this calculation for just a single row, we're doing it for all rows of our design matrix at once. And so the result of that is over here on the right, which is our predicted response vector y hat. And you'll see the second row of this is equal to 0.1, which is what we computed not too long ago, which makes sense. So in order to make predictions for our entire data set, we use this matrix multiplication. For a single observation, you do this dot product. And this slide nicely summarizes these properties. So when we're looking at a single observation, our model is y hat is equal to x transpose theta. And as a reminder, we can also express this as a function of x. Here on the left, x is a vector of size p+1. It contains all of the features for a single observation. For instance, it contains a 1, the field goal value, the assist value, and the points value for a single player. Y hat is a scalar, the output is just one number, and our parameter vector theta is a vector of size p+1. When looking at multiple observations at once, we instead say x with this fancy notation is a matrix of size n by p+1. Y hat is a vector containing all of our predictions, and so it's a vector of size n. And once again, theta is a vector of size p+1. So the thetas in both of these scenarios are the same. These are really the same model, just one only looks at a single observation at a time, and one looks at multiple observations at a time. The way we make predictions for y hat in both models is exactly the same.